thanks. So thanks for having me speak. Right, so last time Arthur introduced the analytic prismatization, and I want to focus on the syntomification. And so maybe let me start with at least some motivation. So I guess one key question in p-adic Hodge theory is how to compare the RAM data and etal data.
Maybe in the end we don't need a microphone. I think it's probably.
Okay.
Yeah, sorry, I apologize.
Again, maybe what I mean by the RAM data is something like, okay, the RAM cohomology. But maybe also the Hodge filtration. Or maybe a crystalline Frobenius. And so on. And maybe on the etal side, we're also interested in the Gall-Reich. On etal cohomology. And sort of the role of syntomic cohomology is supposed to be to bridge these two sides. Right? So this is one way to look at it. And maybe a different point of view still is that syntomic cohomology is supposed to be at least something like p-adic etal motivic cohomology. And sort of let me stress that this is non-A1 invariant. Motivic cohomology, because already like the Hodge filtration is not A1 invariant. Okay, so this is my short motivation. And now, so if I want to maybe I use a different board. So now I want to tell you how to define the analytic syntomification. And okay, throughout I want that X is a Berkovich space. Over QP. And let me remind you, at least briefly, what the basic format of the definition in the Bhatt Lurie setting is for p-adic formal schemes. And this will also be what happens here. So the basic format is the following. First, you define a filtered refinement denoted xn of, well, in our case, the analytic prismatization. And then the second step is to identify two copies of the prismatization living inside this filtered prismatization. So these are usually denoted J de Rham and J Hodge-Tate. And, well, in the end, the syntomification will be the co-equalizer of these two maps. Meaning that we take this filtered prismatization and glue the two copies of the prismatization sitting inside it. Okay. And now, okay, maybe before we begin, I want to recall some things from Arthur's talks. For each nil perfectoid ring A over QP, he introduced the thickening denoted XA of the punctured Fark-Fontaine disk associated to the reduction. And this was defined as a push-out where, well, here I take my punctured Fark-Fontaine disk, and sitting inside I have a countable number of copies of A bar, because this A bar is a perfectoid in characteristic 0. And then I just take the push out along the map from G spec A bar to G spec A. Right? And so the picture is something like this. So you have this Fark-Fontaine disk, and then you have these countably many copies of A bar, where sort of this is now the 0th one, and this is the first and the second, and so on. And you also have these sort of pre-images under Frobenius. So there's a Frobenius on the whole picture, which acts in this direction. And on the positive translates of this sort of 0th copy of A bar, I glue A instead of A bar. Okay. Right. So in particular, this thing is not perfect. And then,
so is XA? This is a sort of derived Berkovich space. Is that?
Yeah.
Okay.
Yeah, I didn't want to. I wanted to gloss over this, but it's the push out in Berkovich spaces. It's not the push out in Gelfand-Sachs. So maybe I should say this in the right spaces. All right, and then, well, we defined. Maybe I continue here. So we defined the prismatization of QP on nil perfectoids as classifying degree 1 divisors inside the space XA, where like the degree 1 condition is asked after pulling back to the Fark-Fontaine disk of the reduction. Right? And then over this QP prism, we defined X prism as, well, first I have to give myself a degree 1 divisor D inside XA, and then I just parameterize maps from D to X. Okay. Right, now maybe I have to switch. So the picture was something like this. So, well, I remind you that on this X prism there was a radius map to 0 infinity. So now this is 0, and this is infinity, where like 0 and infinity are both excluded. And generically, this X prism is isomorphic to its analytic de Rham stack. And the analytic de Rham stack of X prism is the same as the de Rham stack of the Fark-Fontaine curve of X, of the diamond of X. And the only loci where this map from X prism to its analytic de Rham stack is not an isomorphism is over like, the preimage of 1 over p, 1 over p squared, and so on, under this radius map. And in particular, over sort of these points, you have a copy of the analytic Hodge-Tate stack of X. And then if I apply Frobenius one more time, then this Hodge-Tate stack is mapped to the de Rham stack of X. Okay. All right. I think that's what I wanted to say about this. Okay. And so now I want to observe that we have the following map. Maybe a map which I call mu tilde from QP prism to the de Rham stack of A1 mod GM. And this is given as follows. So I have my degree 1 divisor inside XA. And I map it to its pullback along the map. Well, maybe I write this like so. So I pull back along this sort of minus first copy of A bar sitting inside XA. So it's basically the last one where I haven't made, the last one where I haven't made this decay. Okay. And so this gives me a divisor on A bar, meaning I get a point of the A point of the de Rham stack of A1 mod GM. Right? And so, in some sense, you could say that this map from QP prism to A1 mod GM de Rham classifies QP de Rham. I mean, this QP de Rham is not a divisor in QP prism, but okay, this is also the de Rham stack of A1 mod GM. Okay, and the first thing I want to observe is that this map to A1 mod GM de Rham actually refines to a map whose target is the open unit disk quotiented out by the overconvergent torus de Rham. So let me maybe say what this means. So I guess I don't have to say what the open unit disk is, but maybe I should say what I mean by this T bar. So it's supposed to be the overconvergent unit torus. So it's given by G spec of QP, and then I adjoin X and X inverse. And I require that both X and X inverse have a norm at most 1. And this acts on the open disk by multiplication, and I claim that this map lifts along the natural map from here to here. And maybe I don't want to give the proof, but just want to say what this means. So basically this means that whenever I have such a degree 1 divisor, I can remember sort of the norm of the element which cuts out the pullback along this map. So this quotienting out by the overconvergent torus sort of only remembers the norm of the element. And then in addition, I'm claiming that this norm will always be less than 1. Okay, and the reason is that, well, this D is always cut out by a distinguished element locally, and for distinguished elements, you can check this. Like if you have any 2 distinguished elements and they cut out the same divisor, the pullback to A bar, the pullbacks to A bar have the same norm. All right. Okay. And using this map, you can define the filtered prismatization of QP. So again, as always in these talks with rational coefficients, and it's defined as the following pullback. So I take QP prism, and I take this mu tilde map, and well, now I've told you that it refines to a map to the Durham stack of the open disk, mod the overconvergent torus. But actually, sort of to make the formula look nicer, I want to go to the overconvergent disk. I pull back along the following map. So I take 2 copies of this overconvergent unit disk, modulo the overconvergent torus. And for one of them, I take the Durham stack. And now multiplication on this overconvergent unit disk induces a map like so. And this is the map I want to pull back along. And well, this means that this filtered prismatization of QP comes with a map to the disk mod the torus and to the Durham stack of this quotient. And I want to call these maps T and U, respectively. Right. This map I want to call pi. Right, so maybe I should also say that sort of this overconvergent unit disk is just the G spec of this algebra here. Right. Sort of ask that X has norm at most 1.
Sorry, just to clarify, when you say it has norm at most 1, that means it's in some overconvergent sense. It's not the table,
yeah,
right?
So it's in this, like, I think Arthur defined this algebra here.
Okay, yeah.
I can sort of, it's given by all the power series which overconverge on the unit disk. So it's not the same as it's not the same as the Taylor algebra. It's sort of a co-limit of Taylor algebra. And in fact, there's a similar description of the algebraic filtered prismatization of ZP, which appeared in a paper of Gardner and Matapusi. And it's basically precisely the same product. Okay. So now I have to explain to you how to get the filtered prismatization of any Lagrange space X. And so, well, let's first think about what an A point of QP N is. And this is a triple consisting of, I need a degree 1 divisor inside of XA. This gives me a point of QP prism. Then I need an A point of this disk modulo torus, which gives me a map T from some invertible A module to A. And I need a point of the Durham stack of this disk modulo torus, and well, sort of, actually I should say that one of these actions here is by multiplication and one of them is by division. And so this is why I write the map now in the other way. So I get a map from A bar to an invertible module over A bar, which I call A. So note that actually giving a point of this overconvergent disk modulo the torus is slightly more data than just such a generalized Cartier divisor. But actually I won't need this extra data to define the filtered prismatization of X. And basically, maybe I can say what the extra data is. So sort of you have to give a norm on this line bundle L, and this map from L to A has to have norm at most 1. Basically.
Right. What's the compatibility condition?
Right, I was about to say that. Yeah. So the compatibility is the following. So you also have to give an isomorphism. Well, if you take D and pull it back to G spec A bar, then it has to be isomorphic to G spec of the cone of L tensor K dual to A. That's along this map U times T. So in particular, I get the following map. So I start from G spec of the cone of L bar to A bar, where L bar is just supposed to be the base change of L to A bar. And now, using U, I get a map to, maybe I can say, maybe I can just do it like this. The spec of this cone from L bar to A bar maps to this right hand side via U. And then this left hand side, of course, maps to D via the first projection. So now I can go like this, and I have a map from here to here. Okay. And now, given such an A point of QPN, I define something I call D plus. So it's sort of a filtered version of D. And it's the following push out. I take this cone of the map L bar to A bar. It maps to a spec of the cone of L to A, so these are always T. And now here I take this map from here to D, which I just constructed. And this pushout is supposed to be D plus. And again, the pushout is supposed to take place in derived Berkowitz spaces.
Sorry, Maximilian. Sorry. Can you repeat what this map U is?
So it's U on this term and the identity on this term.
U is not. U is a map from K dual to A bar.
Yeah, maybe it's a bit confused. So here I took spec. So on rings, it's a map from this cone to this cone.
Yeah.
And so I need and so from U, maybe I should write U dual. And U dual gives me a map from K dual to A bar. So it gives me a map from this term to this term. And on these, I take the identity.
Okay, cool. Thank you.
And then on spec, it goes, yeah. I see that it's a bit confusing.
Thank you. Sorry, can I ask?
Yeah.
What is the, I mean, if I was to write down the same diagram for ZP diagram,
Yeah,
You
that's
said
what
this
I
would be-
try to indicate.
why
If you-
should this, I mean, I have this notion of admissible W module or whatever. How does
Right,
that?
you can. There's such a Cartesian diagram.
Is this just like some way to unwind what this admissible W module means, or is there?
Maybe I can try to say it briefly. So, okay, this first map is the usual T map that you know. And then the second map is maybe a bit harder to see from this admissible W module perspective. But basically, such an admissible W module was some extension, right? And then you can compute this X group. And like if I take extensions like where I have GA sharp and I have just F lower star W, then this X group is given by GA de Rham. And sort of the second map is given by this X class. Yeah, the compatibility, I think, should then just be that sort of the map you have on this term and on this term induce a map on the middle.
And by the way, this is really as a derived stack, is that right? So my question was that this admissible W modules, maybe it was not so clear how to define them, like to make a derived stack out of them. This is really a.
I mean, if you interpret everything underived, then you can relate it to this admissible W module notion. Any other questions? Okay. Now the definition should be clear. So if I have X a Gelfand stack, I define the filtered analytic prismatization of X, which is a Gelfand stack over QPN, to be sort of the moduli space of maps from this D plus to X.
Maybe you want to restrict to Berkovich space.
I think you can make this definition. I mean, in the end, I restrict to Berkovich spaces anyway. Maybe then I can make the following remark. So with this restriction of X being a Berkovich space, you get a Cartesian diagram Xn, X prism, X cone de Rham, X cone over QP. Well, sort of this map X prism to X cone de Rham is precisely induced by this composite map. Okay. And this diagram is a pullback precisely because this is a push out in derived Berkovich spaces. Okay. And so now the most important result will be sort of using the geometry of, or concerning the geometry of the stack. So let me say X Berkovich space, and then you have the following features. So if you restrict, maybe first I want to remark that because this T was a map from QPN to this quotient by the torus, T has a well-defined norm on QPN because I only quotient out this torus. And so I can speak about the locus where T has norm 1, which is basically pulling back to here. And my claim is that this is isomorphic to the prismatization of X via pi. I can also restrict to the locus where U has norm 1. This is also allowed. And this will also be isomorphic to the prismatization of X. And this isomorphism intertwines pi and the Frobenius on X prism.
So you introduce the notation pi.
I think so, yeah. I mean, I wiped the board. But so pi is supposed to be this map from QPN to QP prism, which only remembers sort of the first entry of this triple.
But no, you want it for X, I guess. Okay.
But okay.
I mean, you can just write it.
Yeah,
that's what I mean.
This is pi.
Can you just remind me what is X cone?
X cone was so it was defined using the ring stack, which sends A to the cone of L. So in general, this is something which lives over A1 or GM, and given a generalized Cartier divisor, it parameterizes maps from this Cartier divisor to X. Okay. Right. So the third one is that I can also restrict to the locus where U has norm 0. So it's diagonal potent. And then I claim that I get the filtered de Rham stack of X. And finally, if both U and T are away from 0, then I don't get anything very interesting. I just see the prismatization, remove the de Rham stack, cross the Betti stack of this closed interval. And this is via pi. Okay. So let me try to draw a picture. So I have two axes, one of which is T and one of which is U. And on top of this picture I have xn. So here is 1, this is 0, 0, 1. So maybe really on these axes I'm recording the norm of U and T. And then my claim is the following. So on this left part, so when U has norm 0, you get X de Rham plus. On this part where U has norm 1, you get a copy of the prismatization. And sort of the map this induces from X prism to Xn, this will be J hot state. On the top here, where T has norm 1, you get this other copy of the prismatization. And this is like the embedding of this copy of the prismatization inside Xn. This will be the map J de Rham. Right. And maybe I should also say that, of course, given my claim that this is the filtered de Rham stack, I have to see the de Rham stack on this corner here. And sort of this de Rham stack here is precisely this sort of first de Rham stack that you see in the diagram. And I also remarked previously that sort of this embedding and this embedding, they are off by Frobenius. So correspondingly here on this corner, you get x hot state. And this is sort of this copy of x hot state, which under Frobenius gets back to x dual. All right. Maybe I also want to say that the locus where both u and t have norm 1 is empty. And this is because this map to the Dramstack of the disk mod the torus from QP prism actually factored through the open disk. And so if both of them have norm 1, then and then, well, this last claim that if u and t both are away from 0, then I just get the prismatization times an interval. This sort of says that along each of these kind of hyperbolas, there's sort of no variation. Sort of each hyperbola is whatever I see here times 0. Right, and this sort of also is consistent with the fact that on the prismatization, Frobenius is an isomorphism everywhere except from x hot state to x dual. And so sort of precisely here you get x hot state and x dual, and everywhere away from these loci you have this isomorphism. Okay. So I want to explain why these things are true. Right, so maybe I should have planned this better and kept the pullback diagram, which defines. Maybe I write it here. So recall this pullback diagram that defined QP prism. And so if I restrict to the locus where t has norm 1, then this bottom map becomes an isomorphism. And so I get an isomorphism on the top. And this gives me the first statement. So 1 is okay. For 2, well, for 2, I'm claiming that that this diagram is Cartesian. Okay. But this just corresponds to the fact that the following diagram is a pushout. So I take this -1 times g spec a bar, it sits inside xa. And I take the pushout along the map from g spec a bar to g spec a. And now sort of, this is supposed to be the infusion of the first a into xa. So this is somehow, you can somehow see this in the picture. So from this basically precisely saying that Frobenius is an isomorphism everywhere except at a bar, where it goes into a. So if I take this push out, then I get xa. Okay. So I guess, sort of strictly speaking, I would also have to check that this D plus comes out the way you want, but let me not do that. It's basically for the same reason. Okay. So for the third part, well, now I'm on u equals 0. So in particular,
this part 2, you have some Cartesian square here. Is it also true as stated in the integral setting if I have A1 mod GMs?
Yeah, that's true. I think that's true. Okay, so for the third part, I want to look at this locus u equals 0. So in particular, I have to look at the locus where this mu tilde map has norm 0. Okay. And the first thing you have to observe is that if you take the locus inside Q prism where mu tilde has norm 0, and this is, well, as I said before, this mu tilde map kind of parameterizes QP de Rham or classifies QP de Rham. And so I'm claiming that this is actually an isomorphism. Well, QP de Rham is just G spec QP. And what's the divisor that's parameterized by this? So the divisor is exactly this minus 1 times G spec A bar. So I have this divisor here. All right. Which means that in this push-out diagram, this is G spec A bar. And also, this map is the 0 map by sort of assumption. Look at u equals 0. So this map is induced by the 0 map. So in fact, you will see that like it's sort of just the canonical map from A bar to the cone. And so this push out, well, it's computed by pullback on rings. And so what you find is that this D plus is spec of the cone of L tensor mil type A. Okay, and this is precisely the ring stack which gives me the filtered analytic drum stack. All right. And then maybe let me say something about the last part here, because I want to be brief. So for this last part, I'm looking at the locus where u and t are away from 0. And now the key is that if I take the punctured overconvergent disk and I mod out the torus, it's just the Betti stack of 0, 1, sort of induced by the norm knob on the disk. And so this means that on this locus, I just have 0, 1 times 0, 1 here. And then you have to twist by some automorphism of this thing to get that.
Visualize question. Yeah. So when you say the absolute value of u is equal to 0, I mean u is still there. Does it show up? I mean it must show up.
It's not there anymore in some because I mean u was some map to this de Rham stack, and so if I sort of restrict to this part, then I take the de Rham stack of GA dagger mod this, which is just the classifying stack of T bar. Right. So this explains why the u disappears here. And I only get the T, which comes from this. Because somehow this line bundle here is determined by, well, the line bundle sort of in the T direction and this line bundle I get myself here. Okay. All right. Any other questions? Okay. And so, okay. Now you've, if you've made it to here, then we are done with like the most difficult part of the definition. Because now, as I said in the beginning, sort of it's going to be very easy in that if we take, again, X a Berkovich space, then again, sort of the rational analytic syntomification of X is the co-equalizer. Well, I have X prism, and using this part 1 and part 2, I get two maps. Let me say this again. So here I get a map J Durham from X prism to Xn, and here I get a map J Hodge-Tate, which also goes from X prism to Xn. Yes. So.
I just want to ask in part 4, why is 0 still included on top?
It's because you have to twist by some automorphism here, and I think it's clearer from the picture that I drew earlier.
Okay, sure.
Which was this one. I mean, I'm just claiming that on the level of topological spaces. Sort of if I take this multiplication map, then sort of this thing, I can apply some non-trivial automorphism here so that this becomes the first projection. So basically, on the first coordinate, it's multiplication, and then on the second coordinate, you have to do something that remembers sort of the ratio between U and T.
Okay, thank you.
All right, so we have these two maps, J Hodge-Tate and J Durham. And I take the co-equalizer. And then, well, this category of quasi-coherent sheaves on X sin is the category of analytic prismatic FKs. On X. And so sort of in keeping with the motivation from the beginning, you should perhaps think of this as some category of analytic p-adic étale motives of X. And so in particular, as in the integral theory, any map f x to y of Berkovich spaces, I can look at the push forward of the structure sheaf along the induced map of syntomifications, and this gives me something here. So it gives me a prismatic f gauge on y, and this is kind of like the motive of x over y. Right. And so maybe I should also tell you what sort of the Tate twist is in this category of motives. So I take the universal Cartier divisor on this disk mod the torus. So I use this funny angle brackets because sort of the round brackets already have a meaning on the Fark-Fontaine curve, and maybe I don't want to get confused. And then I define the Poisson twist maybe first on the filtered prismatization as the tensor product of the pullback of the Breuil-Kissin twist on the prismatization along this pi map with the pullback of this O-1 along T.
What's the universal Cartier divisor on this
maybe I want to say that like this maps to A1 mod GM, and this O-1 is the universal line bundle of the classifying sync. All right, and sort of you can check that this descends to the syntomification. All right. Yeah. And using this, you can now say what syntomic homology is supposed to be. So have X a Berkovich space, then I can define the rational analytic syntomic homology of X. In weight I. As well, I just take cohomology on X sin of the ith power of this Breuil-Kissin twist. So I pull back the Breuil-Kissin twist from QP sin to X sin, and then I take the ith term power. Right. So there are two more things that I want to say.
Do you know that this definition of syntomic homology coincides with like older definitions of syntomic homology for rigid spaces?
If X is a smooth Berkovich space, then over QP, then this is true.
Okay.
And we'll see why in the second part.
It reduces to some local calculation.
No, you can. I'll make a remark in the second part, okay? Yeah. Basically, the answer is that you can compare this with like filtered Ram homology and Hyodo-Kato homology via these stacks, and sort of conditional on the expected theorem that X Hyodo-Kato computes Hyodo-Kato homology, you get also this.
But that's is that known? Oh, okay, sorry, I don't know.
It should be true. Okay, so I want to make one more definition and one example. And so the definition is, so let's take a perfect F gauge on X, so a perfect complex on X sin. And then I can consider the pullback along the following map. So X sim receives a map from the filtered prismatization of X. And well, previously I told you that if I take the locus where U has norm 0, this identifies with the filtered de Rham stack of X. So there's a map from X de Rham plus to Xn. And so in particular, I can restrict this to I call this the Hodge stack of X. It's, I think, not the same as the Hodge stack in Arthur's Hauck. It's a bit unfortunate. I'm sorry about this. It's what you get if if you base change this filtered Rahm stack to the locus to the vanishing locus of T. So if you base change this along the map from point mod GM to A1 mod GM.
So modules on it are like Higgs modules and stuff.
Exactly, yeah.
At least with the definition you give, how do you make sense of saying that the F gauge is perfect?
I mean, there's a notion of perfect complexes on any Gelfand stack.
Okay, so
And it satisfies descent and sort of on affines, it's so. If you have an affine Gelfand stack, it's the same as perfect complexes on the underlying discrete ring of A.
and then you define it.
And this, sort of, it's a theorem that this thing satisfies descent for discrete topology.
Is it also the same as dualizable objects in quadratic?
Yes, it's also the same as dualizable objects. And this is why it satisfies descent. All right, so okay, let me clean up this mess I made. Right, so you have this map, and this Hodge stack receives a map from X times the classifying stack of the torus. So I mean, usually it would be point mod GM, but because I'm working with the torus everywhere, this is the torus.
The map from X Hodge to X Nygaard comes from, but it's inside the wrong place. So it's the locus where U and T are both 0.
Yeah, exactly. So it's in the picture it's here. Okay. And so what did I want to say? So so if I pull back along this composition, then this E gives me a graded perfect complex on X. This here. Maybe I want to call this the M upper bullet on X. And the Hodge tape weights of E are those integers I such that this graded complex is non-zero in degree I. Okay. And maybe I can fit my example down here. So the ith Poikiss interest has Hodge tape weight. Well, it depends on your normalization, if there's a minus sign or not. Maybe I want a minus sign, then it's minus I.
So if you wrote point mod GM there, I would understand why I would get a graded complex. But
Yeah, and now you should think of this as maybe this is why I restricted to perfect complexes.
okay,
So my point is that if you have a perfect complex, then perfect complexes on this are the same as perfect complexes on point mod GM.
okay, so you can use the perfectness
And,
condition
yeah.
later too.
So this is why I only made the definition for perfect F gauges. Okay, I think now is a good time to make a break. All right. So in the first part we saw the definition of syntomification. And now I want to discuss the case of GM. And sort of, my goal will be to describe the filter prismatization of QP and that of GM somewhat explicitly as quotient stacks. And for this, the first thing that I want to note is that this here. I have a radius map just because I X prism has a radius map, and I have a map from Xn to X prism. Sort of Xn also obtains a radius map by this composition. And also previously I had the statement that if I localize away from u and t equals 0, then I just see the prismatization. And this is, well, this ut not equal to 0. Should I say this? Maybe I should say that. So I only have to understand some neighborhood of this locus where u times t has no 0. And this thing is fully contained inside the preimage of P under sort of this map. Because u times t equals 0 corresponded to like taking the Durand point in the prismatization, and the Durand point is supported over P. So it suffices to understand this xn in some neighborhood of P inside 0 infinity. And more explicitly, the one that I want to take is the one from root p to the 3, not including the ends. And okay, maybe there's just one slight problem. I don't really know how to do this for Drinfeld prismatization directly, and this is because this map that I had before, like from so basically, what should the strategy be? I mean, I have this pullback, and Arthur last time gave some description of QP prism using like the Q-Durand prism, and now the problem is that this map here, so this Q-Durand, so it involved some kind of ZP cross-action on the Q-Durand prism. And the problem is that this map here does not play very well with this ZP cross-action, because basically, if I take the Q-Durand prism and I take this composite map, then I land here. And if I act with some element in ZP cross on this thing, then it's super hard to describe what the image just in terms of this fraction without knowing Q. But the situation gets much better if I go down to a 1 mod GM Durand, because then, at least in this sort of locus from root P to the 3, this thing identifies with log Q. And sort of, because now I'm allowed to work up to units, and before I was only allowed to work up to units of norm 1. And sort of clearly this will not have the same norm as this, but up to units in this open locus, these are the same. And this log Q interacts much more nicely with the ZP cross-action, because, I mean, it's exponentiation on Q, so it's just multiplication on log Q. And, all right. So this was motivation for, maybe I keep this. So it's much better if I replace QPN by a variant which I denote by QPN bar. And in this variant, all quotients disks not torus are replaced by A1 mod GM. And you can also convince yourself that it's not too bad to do this, because I mean this QPN maps to QPN bar, and up to, well, this map is basically a torsor for the Betti stack of 0 infinity, up to restricting to some closed substack. So in particular, if I want to use this presentation to understand things like cohomological smoothness of QPN, understanding this reduced version is good enough. Okay, and now let me also say that Xn descends to Xn bar over QPN bar. And this is because previously in the definition of this D+, I only needed to use the generalized Cartier divisors that I was given. And I didn't use anywhere that they had a norm or that they had norm less than or equal to 1. All right. And so now, for this QPN bar, I can give the following description. And maybe it's going to look a bit nasty, but okay. So basically, if you unravel this pullback diagram, what you get is the following thing. Maybe I should have taken more space. All right, so, okay, as I said, it looks a bit nasty, but it's not so bad. So what do I get? I get A1 times A1 de Rham, which comes from like this bottom left part of the pullback diagram. And I fiber with this perfected Q de Rham prism, base change to this sort of open locus, which I'm considering, over A1 de Rham. And what are these maps? So this map is multiplication. And as I said before, this map here is log Q. And okay, so now I quotient out by some group action. And the group I'm considering is, well, the push out in abelian group stacks of ZP cross LA and GM along the common copy of GM dagger. So GM dagger sits inside ZP cross LA as the overconversion neighborhood of 1. And the action is the following. So ZP cross LA acts on A1 by multiplication, by which I mean it acts on this A1. It does not act on this A1 de Rham. So this thing, the action on this one is trivial. It acts, of course, on this Q de Rham prism by the usual formula. So I send I just exponentiate. And GM, well, it acts on A1 de Rham by division and on A1 by multiplication. Okay, so this is the thing that I said before, that sort of on on T, I want to act by multiplication, and on U, I want to act by division, because in the end, they somehow correspond to filtrations going in opposite directions. And so maybe let me also say why this gives you a well-defined action of this push-out. So the main thing to observe is that if I restrict this this division action of GM on this de Rham stack to GM dagger, I get the trivial action, precisely because I take the de Rham stack here. So this action actually factors through the de Rham stack of GM. And so sort of the action on this A1 de Rham of GM is trivial, and this matches with the fact that ZP cross LA acts trivially on this A1 de Rham. And sort of now you precisely see what I said before, that this usual action of ZP cross on the Q de Rham prism is very nicely compatible with this log Q map, because I just get multiplication on A1. All right. And maybe I should also say that you can also get rid of the de Rham stacks in the numerator. So you can turn this into A1 cross A1 and fiber over A1. But then you need to quotient out by some slightly more complicated group, and I didn't want to spend the time on writing it down. And okay, maybe I just briefly say something about the proof. So, well, you should observe that on this locus, to which I've restricted, the prismatization is just isomorphic to its own de Rham stack. And then, as I said before, you use this definition of QPN as a pullback, and you use the Q de Rham presentation. Of QP Hieropat. Maybe I don't want to say anything more about this. It's a computation.
In terms of pictures, I always have difficulty visualizing what the radius map does in terms of your picture. Is it
this picture is not really suited to thinking about the radius map, I'd say. Or maybe, I guess the radius map, like definitely all these hyperbolas are in the same fiber of the radius map. Okay.
Maybe everyone knows this, but what is the Q de Rham presentation?
Maybe I can write it so it's like. You take this open disk around 1.
Oh, okay.
You take the de Rham stack of this, and you take the perfection, remove 1, and then you mod out by QP cross smooth. Right, so now let's do GM. And I want to work over. So I want to keep working over this locus, and I now also work over.
This like square root of p and 3/2 power of p is just some choice.
I think it's sort of the largest interval where you can make this work, because I mean, you need this q to the p minus 1 over q minus 1 to be log q up to a unit after pulling back to g spec a bar, and sort of as soon as your one Frobenius twist further, this fails. So somehow you have to pick an interval where you don't have 2 points which are identified under Frobenius.
Are things any more subtle at p equals 2? Or?
I haven't thought about it. Probably not. I think not. All right.
Is P assumed to be greater than 2?
No, phi can be 2. Phi can be 2. So I consider this reduced filtered prismatization of GM. as with the prismatization, I can write it as a quotient of the perfected GM over the space. And the quotient is, again by some push out, so I take ZPLA and I take the push out with GA dagger over GA dagger, where like this map GA dagger to ZPLA is just the inclusion of the overconversion neighborhood of 0. And this map here is supposed to be multiplication by U. Where sort of maybe to make sense of this, you actually have to get rid of this gram stack first, as I said before, to make sense of U. And let me also say what the action is. So if I take some theta in ZPLA and some V in GA dagger, then I act on x to the 1 over p to the m by multiplying with q to the theta over p to the m, where this q comes from the q Durand prism on the base. I multiply by the exponential of tv over p to the m. And so now, for this exponential to be well defined, you can observe that v is dagger nilpotent. So this whole thing is dagger nilpotent. And so somehow this, like if I just take this thing, then it's more like the filtered Durand stack of GM, because I have this t rescaled version of the exponential. If I just had this, it's the prismatization of GM, and somehow I mixed the two. And this, let me not say anything about the computation. Like you can compute it just from this pullback diagram. Xn, X prism, X cone, X cone Durand. So you use the presentation you know for GM prism, and then you can deduce this. Okay. And maybe one nice consequence, or one very explicit thing that you can deduce. So we can use this to describe perfect complexes on the locus where T has norm 0 inside the filter prismatization. If we have a toric chart of X. So maybe let me say that in the future I will denote this thing by sort of a slightly clunky notation X hot state dagger plus, because it's like a filtered version of the overconversion neighborhood of X hot state inside X prism. So namely, if I take this thing and also restrict to the locus where U has norm 1, then it's precisely the overconvergent neighborhood of X hot state inside X prism. And sort of now I have this extra U variable, which is kind of like a filtration. Okay. And so what's the statement? So putting myself in this situation here where I have a toric chart, I can make the data of a perfect complex on this X hot state dagger plus very explicit. And it amounts to the following data. So first I want a diagram like so. where each fill IV is a perfect complex on something I denote x infinity LA cross G spec QP zeta P infinity cross G spec QP R dagger. Right, now let me explain what this means. So R is supposed to be U times T. And x infinity LA is the base change of sort of the standard perfected cover of the torus along this toric chart. Okay. So I have a diagram like so, and maybe you should think of this as like a version of the hot state filtration, like the filtration in the U direction. Okay. I want linear maps D from fill I to fill I minus 1, which satisfy du is ud plus 1. So it's like a derivation in the u direction. I want a T connection on V. So this means a map like so, which satisfies nabla of Fm is F times nabla M plus T times dF times M. Maybe I should say dF dt times M. And this this should have the property that if I restrict to fill I, it factors through fill I minus 1. And right, this twist by minus 1 indicates that ZP cross acts on this thing by division. And if you do this twist, then this map is supposed to be ZP cross equivariant. All right. So we're almost done. So I want a semi-linear locally analytic ZPN cross ZPN cross ZP cross action on this filtration where ZP cross acts on ZPN by multiplication. And now perhaps the most important part is that this locally analytic action should be compatible with this derivation D and this T connection nabla. In the sense that I get sort of an arithmetic Sen operator if I restrict to the action of ZP cross and take the derivative. And I get an arithmetic Sen operator which goes from fill I to fill I. And I want that this identifies with ud minus I. And I also have a condition on the geometric Sen operator, so I can also take the derivative of the ZPN action And then I get a map from fill IV to fill IV tensor this thing. And this is supposed to identify with U times Nobler. So maybe this is just a fancy way of saying I have this semi-linear locally analytic action, and the arithmetic Sen operator is multiplication by minus I on GR I, and the geometric Sen operator on fill I factors through fill I minus 1. Sort of the factorizations you get are given by this D and this Nobler. And basically what this tells you is that the linear algebra structure you see, at least on this locus, is something like a compatibility between like a connection on some filtered vector bundle and the geometric Sen operator, for example. Maybe I can also make this a bit more explicit by saying that well, I can restrict from this filtered thing to the unfiltered thing. And this just corresponds to forgetting, so I take the co-limit along U and I forget D. But maybe more interesting is what happens if I restrict to the locus where both U and T have norm 0. So I can do this, and this is isomorphic to the norm T equals 0 locus in the filtered Ram stack. So I should get a filtered perfect complex with connection. And how this works is, well, you take the ith graded along these U maps, and then you twist by I. And afterwards, this condition 5 tells you that now the arithmetic Sen operator on these, so this is a Tate twist, by the way. So this tells you that the arithmetic Sen operator on these things is trivial, and also the geometric one is trivial. And so I can descend this from this x infinity LA cross QP zeta P infinity to x. Precisely because both of these, precisely because this action now becomes a smooth action on these graded pieces. And this is a torsor for the smooth incarnation of the semi-direct product over x. And so then this thing descends to x, and well, this T connection factors through T, so I can divide by T. Oh no, sorry. So the T connection now induces something from GR I V I to GR I minus 1, V I minus 1. So now I've also taken care of this twist by minus 1 here. So this sort of naturally becomes incorporated here. And now on these graded pieces, I still have this T map, which gives me a filtration. And so I end up with a perfect complex with a filtration and a Griffith transversal connection.
Sorry, this is a lot.
Yeah, sorry.
It's, but I just pick up a very basic question. Just so one is like in coming up with this. I mean, was there some analog in the integral setting? I mean, so
yeah, you can find like certainly this thing has an analog in the integral setting. Like this is like this is the Sen operator on the integral, say, filter or even prismatization of ZP, this D. And basically this filtration is the conjugal filtration, I think. And then this Sen operator has a compatibility with the conjugal filtration.
So if X is exactly QP, then does this look kind of similar to some of the structures that are?
Yes. Yeah.
Okay.
Yeah.
And maybe sorry, it does require but still you're taking the product with the spec of QP adjoint zeta p to the infinity, so maybe that's a bit different.
This is this usual thing where, like, in the analytic setting, you always have to take all p-power roots.
And then descend via the
Like basically, I mean, this comes from the fact that already for the Hodge state stack you need to take all the p-power roots of unity. And so this is supposed to be some kind of filtered and thickened version of the Hodge state stack. So.
Also, my other question was, so some of these structures, they sound a little bit similar to what Lurie was talking about earlier today. And is that true? Or maybe will you explain this later? Or?
Yeah, I think you can. I guess one thing that he said was that this geometric Sen operator has some compatibility with the Hodge state filtration, and this is precisely this thing that it's on fill I, it's supposed to factor through fill I minus 1.
Maybe observing as well that the RAM local system will give rise to.
Right. So this is something that I'll say tomorrow. Whenever you have a Durham local system on X, you get a vector bundle on the syntomification.
Do we expect the converse is true? Like any Durham local system?
It's an equivalence of categories. Okay. Any more questions? Yeah, maybe the point is not to unravel all of this, but just to see that you can make some description, and some of this description is about some compatibility between the Sen operator and some filtration and some connection.
Ask what a morphism of these sets could look like.
Maybe not. Yeah. Yeah, I mean. Okay, so I hope in the remaining time. What I'm going to say will be a little bit less involved than this. So I want to say something about comparison theorems. And so for this, sort of recall that I said in the beginning that symptomic homology should relate étale and Durham dating. So in particular, there should be some comparison to étale cohomology or pro-étale cohomology, and some comparison to invariants that are sort of Durham in one sense or the other. And so you have the following theorem of Kolmes-Anisiol. So let's say X is a smooth, partially proper rigid space over QP. And then they tell you two comparison isomorphisms. So there's a Pullback square, which, okay, maybe strictly speaking, they define some notion of syntomic homology, which we don't yet know that it's the same as this one. And they tell you that this thing is a pullback of some Frobenius and monodromy eigenspace on Hyodo-Kato cohomology.
Subscript is sin OV.
This is sin Cn for Kolmes-Anisiol.
Oh, I see.
Somehow I want to emphasize that it might not be the same. But you can run. And I take the fiber product with the ith stage of the Hodge filtration.
This is some version of this balancing fibers.
Yes. So this is the first part, and the second part is that there's a natural map from syntomic homology in weight I to pro-Ital homology of the ith state twist, and this induces an isomorphism if I truncate up to I, so in low degrees, depending on this I. And so we can recover and generalize this theorem using the syntomification as follows. So if X is a smooth Berkeley space over QP, then I can describe the category of perfect complexes on the syntomification in terms of perfect complexes on the Hurokata stack and perfect complexes on the filtered prismatization, on the filtered round stack. And sort of this gives me a fiber square like in 1, if I take homology of the ith-Breukian twist. Okay?
Just remember, you get an equivalence and not like.
Yeah, it's an equivalence. Yeah. It's an equivalence. And so this is sort of the RAM aspect. And I can also make an Ital variant of the statement, which is that I can swap out this Hurokata stack for xdiff1. And then instead of the Durham stack, I write this overconvergent neighborhood of x hot state inside x prism. And then I have to write this x hot state dagger plus thing.
How exactly would I go formally about deducing one down there?
So, I mean, well, given that we don't know that this is the same as,
anyway, assuming.
but you take R home from the unit.
Okay.
Like you take OI and you take R home from O to OI, and I'm sort of, well, this gives me symptom like homology of OI on Xn, and I'm claiming that here you get exactly this kind of eigenspace on Hurokata homology, and here you get the ith piece of the Hodge filtration. Right.
Would say a little bit about how this works when X is QP. How the theorem works just when X is QP.
When X is QP.
I was wondering because I think the
I can say
really is a fully faithful inclusion, right? It's not an equivalence, but and you're saying it is an equivalence.
I mean, do you want me to explain how the proof works with XQP or the statement?
Maybe just a statement, yeah.
Or maybe I can give the following special case, and it's for vector bundles instead of perfect complexes. So the equivalence respects like tau amplitude, so also works for perfect complexes. And then I get that it's equivalent to, like the first part tells me that vector bundles on QP sin is equivalent to filtered phi n Galois modules. Sort of because on QP de Rham plus I get a filtration, and then vector bundles on QP Locato are precisely these phi n Galois modules. And so in particular, sort of going one step further, I see that this is the same as maybe I should say Galois equivariant vector bundles on the Fark-Fontaine curve of CP, which are in particular, like the Rham representations sit fully faithfully inside here. Maybe if we're already talking about the Rham representations, sort of applying this pullback square to QP tells you that if I have V, a de Rham representation of the Galois of QP, then and I view this V as a vector bundle on QP sin via this equivalence, and this H1 is precisely H1G. Because basically you can compute this X group in the Rham representations in terms of filtered phi and Galois modules.
So sorry, just to clarify, H1G means X of the Rham.
Right, it means X in the Rham representations.
If you wanted to then somehow find like H1F, for example, is H1F
I mean, this is
close to this in this, like in this world, is H1F close or far from what in this setup? I know in reality it's not far from H1G, but kind of formally is it?
I don't know. Like you.
Sorry, is H1F for crystalline representation?
Yes.
So I thought that this is something that was in the F gauge, like for
Right.
ZP set.
So if you take the algebraic syntomification of ZP, then H1 is H1F.
Tensor Q at least.
Right, after inverting P. Yeah. And
So for example, are there maps between all the theories that induce the map from H1F to H1G?
I mean, maybe we're not so sure yet in how far there's a map between these two things. But philosophically, yes.
And if you were to take the dual to get H1E, can you sort of see H1E in a meaningful way?
I don't know. I would like to know, yeah.
Because
So
you have some logs and things, I mean, you have various things.
Yeah, you could hope that somehow this H1E,
For example, the
you can see in terms of some compactly supported cohomology on this QP sin, but I haven't been able to produce a clean
how about if we have H1G, maybe we see a dual exponential map on H1, like the Blockato dual exponential, maybe it lives on H1G.
Yeah, I don't know how to see the H1E.
No, but you have but one of these but something receives the exponential map, and then something else would kind of have it be the domain for the dual exponential map. So maybe H1G is the domain for the dual exponential map since it's the dual to H1E.
I think sort of in.
So I wonder if you see.
You can view you can see the exponential map as in this diagram.
Yeah. Okay. So it's living over here somewhere.
Like this is already something that I think Nisio maybe proves.
It's a boundary map, right?
Yeah. All right.
Does this item 2 give you a different Cartesian? It gives you a different Cartesian square.
Yes. I was going to say something about 2 because right. So maybe let me say first that from 1 you deduce that for smooth, partially proper rigid spaces, this symptomic homology using the stack is the same as this one. And so you would like to say that from 2 you can deduce something like this. So maybe let me say how this works. So maybe first let me write down the actual statement. So the theorem is if X, as before, is a smooth Berkovich space, and E is E is a vector bundle F gauge. With hot state weights at most minus I. And then, well, the first statement is that there is a natural map maybe I should say two things. So, my first claim is that given such a vector bundle, there's an associated vector bundle on X diff 1, basically by Pulltag, which is like comes from this equivalence. And then I get this induced map on cohomology. And if I have this condition on the hot state weights, then it's an isomorphism on this truncation. So in particular, I can imply this to the ith Breuil-Kissin twist. I said before that this has hot state weight minus I. And then I recover this statement.
Is this amounting to some statement that the map from X hot state dagger plus to X hot state dagger is like an isomorphism of cohomology?
Right. So let me say briefly how this works. So, well, what you have to show is that if I take this map on cohomology here, I mean, I get the same Cartesian diagram as in the de Rham case, just with like these terms. And my task is to show that this co-fiber is in degrees greater or equal to I plus 1. And I'm claiming that, well, I mean, this is an assertion that you can check locally. So I can assume that X has a toric charge. And then you can use this description of these categories that I had before to explicitly write down some double complexes which compute these cohomologies. And you see that like the condition on the hot state weights exactly gives you this thing. Now it's an explicit computation. Okay.
Sorry, maybe just again, this sort of heuristic. So I think that there was an idea that like an F gauge in for a formal scheme is something like a refinement of a crystalline Galois representation on the generic fiber. And so as a result, sort of saying something in the same vein for syntomification of regular spaces, but maybe instead of a Galois representation, instead of a local system, you have a vector bundle on the Fark-Fontaine curve.
Right. So I'm going to say this more. But right. So basically, the idea is that you should replace crystalline by de Rham, and then because we're working with rational coefficients, you don't need to do any enhancement. Like it's just a de Rham representation or de Rham vector bundle on the Fark-Fontaine curve. There's no additional data. And then I have 2 minutes or so. Maybe let me try to say why this is true. And it's a geometric argument. So maybe the 2 minutes I have. I want to draw a different picture of this thing, where if I have the two copies of J of X prism sitting on the left and the right, and sort of my radius map goes to here. I have 1 p squared, 1 over p, 1 over p squared, and meaning that so be careful. Here I have And so over P, I have x hot state and x to run. And sort of this part is the analytic, the filtered Rahm stack in this picture. And this is u equals t equals 0, where I have some funny degeneration happening. And then I see the hot state stack. And sort of away from this degeneration, I have the hot state stack times an open interval. And so sort of all the interesting stuff happens at this point where I degenerate from hot state to Lurie. Right? And then sort of I have further copies x hot state, x hot state, x to Rahm, x, this should be x hot state. So downwards I always have hot state stacks, and upwards I always have the Rahm stacks. And these maps are the interval. Like these lines are the intervals that you see in this picture. They're the hyperbolas, basically. And so if I stay away from this part, then here I just see an interval times the prismatization. And so now what's the idea? I have, say, a vector bundle on the full thing. Maybe I should say that to get the syntomification, you glue along Frobenius twist, right? You glue this to this, and this to this, and this to this. That's the idea. So now I have a vector bundle on the syntomification. And now the first idea is that basically I can ignore all the bottom part. Because if I go from here to here, I have an interval, and any vector bundle is constant along an interval. And then this part is glued to this part, so I can forget what's down below. But then I have an interval again, and then I glue this to this, so I can also forget this part. And so in the end, I can focus on this part of the picture, where I don't see these hot state stacks on the bottom anymore. And I just need to, I want to say something about this Rahm version of the statement. Okay. Now I just need to get rid of this hot state stack here. And how do I do this? Well, the second idea is that if I have, say, a vector bundle on the overconvergent neighborhood of some divisor, it always spreads out to some open neighborhood. And so if I have a vector bundle on this thing, then maybe what's the key claim? The key claim is, well, first it's the same as having a vector bundle on just this degeneration, which is compatible with the rest, like away from the degeneration. And away from this, I always see just an interval times whatever's on the right or on the left. Okay, so this part away just sees the Rahm stack of the prismatization, which is like the Hurtado stack. And sort of the Frobenius descent comes from the fact that in the end I glue this thing along a Frobenius twist. So this gives me the Hurtado part of the picture. And so now I have to deal with a perfect complex on precisely this thing. But now, basically the idea is that I can retract this part, because it's just an interval again. And so in the end, I'm left with this thing, and this is the filtered Rahm stack. So this was the 5-minute version. And what I'm saying is that sort of, for the second part, you do the same argument, but downstairs and not upstairs. Okay, thanks.
So, any questions?
Well, I assume we're supposed to, at some point in the future, be like an integral version. We have integral version. In that case, this Bill's and fiber square does not work integrally, so I would not expect your first equivalence to work integrally. But would you still expect some version of your second? Is it truly a rational phenomenon, or is it some?
No, I think the second thing just goes through if you replace also this with an appropriate integral version. Well,
Sorry,
but x is still over qp.
integral here means the coefficient.
Integral,
Coefficient,
right.
yeah.
Integral means the
Yeah,
coefficient.
coefficient,
Yeah.
yeah.
Just x is still over qp. And it's basically because somewhere in this argument I sketched, everything happens sort of here, where you see like the degeneration from x to round to x hot state. And if I do integral coefficients, I see some additional stuff down here at p equals 0. And somehow this additional stuff does not disturb the argument that goes on up here. But you also see why the first part doesn't work anymore, right? Because the first part somehow uses that you can ignore what's happening down below. But this only works if you don't see this p equals 0.
I guess the plan is that you'll continue. Oh, sorry.
It's a naive question. So if I want to be integral in the spaces, do I get like 1 and not 2 or something?
Maybe maybe I can make the following statement. So if x is over fp, but the coefficients are qp, then the syntomification just sees the Hurley-Kato stack.